Welcome back, AP Stat. This is the fourth and final part of Chapter 18. We're now going to be doing something a little bit different. We'll be modifying one of the formulas you've learned to find a sufficiently large sample size. So given a desired margin of error and confidence level, we can find an adequate sample size. So to shrink our margin of error for a given confidence level, so we keep the same level of confidence and shorten that margin of error for a more precise guess for our interval estimate, we need to increase the sample size. So you're familiar with this formula. The margin of error is equal to z star times root pq both hat over n. All right? So that is our margin of error for our confidence interval. Now what I'm going to do is a bit of algebra, okay? If I were to solve for n, I would get n equals p hat q hat times the square of the ratio of the z star value over the margin of error, okay? This is a good formula to put to memory. Yes, you can derive it with a little bit of algebra from a formula that you would be given on the AP test in the formula sheet. But this, and just putting this to memory, it's not terribly hard to memorize. I recommend you do it. All right, p hat q hat times the square of the ratio of the z star value, the critical value over the margin of error. If we are not given a p hat, all right, if we do not have a pilot study, if we don't have a study we can refer to that gives us a guess at the true population proportion, a p hat value, we can use p hat equals 0.5 to be safe. Now, why is that good? It's because it maximizes the sample size. If we want to be guaranteed a certain level of confidence, and what sample size will do it? Well, the largest that p hat times q hat can be is 0.5 times 0.5 equals 0.25. Any other configuration of p hat and q hat would produce a lower value. So let's apply our new formula. In a March 2016 survey by Gallup of 1,019 U.S. adults, 65% believe that global warming is due more to human activity than natural changes in the environment. The poll reports a margin of error of 4%. Suppose an environmental group was planning a follow-up survey of voters' opinions on global warming and wants to determine a 95% confidence interval with a margin of error of no more than plus or minus 2%. So we want to improve our margin of error, make it smaller, get a more precise result without sacrificing quality. We want to be 95% confident we're going to catch the true population proportion. Question: how large, that is, a sample does the group need? We know the likely, 95%. How large a sample does the group need to get that 95% accuracy? Now, we could use p equals 0.5. That would make it absolutely certain we could keep 95% certainty of catching the true population proportion. But we have the luxury of a prior study. We can use p hat equals 65%, and that will allow us to reduce the sample size without sacrificing the quality of the interval. All right? So here's how we would do this. N equals p hat, 65%. All right, we use that value from the prior study, and the subsequent 35% for q hat. Since it's a 95% confidence interval, we use 1.96 for our critical value. That's how many standard errors we would want to go to the left and right in a confidence interval. And we divide by our margin of error, 0.02, okay? And then we square, okay? Then we square. We're squaring this whole fraction right here. That's going to be equal to 2184.91. Now, I'm going to quote Dr. Seuss here. I'm going to quote Dr. Seuss probably several times. A person's a person no matter how small, okay? So if this is the least number of people you could sample to get the desired accuracy, you gotta round up. No such thing as 0.91 of a person. 9/10 of a person's a person no matter how small. So we would say 2185, we round up, that would be our sample size. Okay, so if you see 2184.0001, I don't care, can't round down without sacrificing accuracy, so you gotta round up. Does not matter what this number is, round up. All right, so credit card company is about to send out a mailing to test the market for a new credit card. From that sample, a company's managers want to estimate the true proportion of people who will sign up for the card nationwide. Here we go. We got a pilot study again suggesting about 0.5% of the people receiving the offer will accept it. That's probably pretty accurate. To be within 0.1 of a percentage point, wow, that's really accurate, of the true rate with 95% confidence, how big does the test mailing have to be? It's going to be a really big number. Pause the video, try this on your own, use the formula, same as last time, and remember, we don't have to use 50% for P hat and Q hat if we have a pilot study that gives us a value for P hat, all right? And we can get a value from Q hat from there, okay? So give this a go, pause the video, unpause the video when you're done. Okay, I'll assume we're ready to continue. Here's the answer. N is equal to P hat 0.005, that's 0.5%, times 0.995, that is the odds of failure, that's Q hat. And we got 1.96 standard errors to the left and right of the sample proportion, and we have our margin of error of 0.001. So we got our critical value and our margin of error. We square that, and we get, oh man, and a decimal. Remember, there's no such thing as 96% of a person. A person's a person no matter how small. We would say 19,112. Now, you may be wondering, what if we were not allowed to use 0.5%? What if we had to use 50-50? What if we had to use 50% for P and Q? What if we did not have a pilot study? Well, if you did not have the pilot study result, you would need to use P hat equals 0.5, Q hat equals 0.5 subsequently, which would yield a sample size of almost 1 million, okay? And for many states and countries, this would constitute more than 10% of the population, which means we would break the rule for not exceeding sampling 10% of the population. You can't assume independence if you sample more than 10% of the population. So literally having a pilot study saves us, all right? We are able to do this problem with a clear conscience with no qualifiers because we have a pilot study. So this is one reason why we can use pilot studies. Makes the problem, this is going to have to be a lot of surveying. However, it's a lot easier than that. And there you go. Hopefully that lesson makes this homework a little easier too.